Alright, we have done a confidence interval and hypothesis test for one sample proportion. Now we're going to do the same thing using two proportions. So we're not talking about where one parameter is or the other, but if they are close to each other or are they different. The same inferences that we use can be used for one for two, because even if the populations are equal proportions, the samples may be different, and we need to find out if the difference is real or just due to sampling. Confidence intervals are one way we can figure this out. The comparison of two population proportions is based on the estimator, P1 hat minus P2 hat, the two sample proportions. That will be the point estimate we use to do our confidence interval. The statistic is used to estimate the difference between the two parameters, which would be P1 minus P2. Okay, basic approach. We do the same thing we did before, the basic steps for confidence interval, and find the difference in proportions. Then we have an extra step when we're talking about two. We check to see if 0 is included in the interval between these two. If it is in the interval, that suggests that the two might be the same, because if P1 minus P2 equals 0, then that implies P1 equals P2 and the proportions would be the same. If 0 is not an interval, the confidence interval tells us which one of the proportions is maybe larger. In other words, if they're both positive or both negative, that can indicate a difference. The confidence interval has the same structure as it did for one proportion. We have a point estimate, which again is P1 hat minus P2 hat, and a margin of error. Z star, same as we had before. We use the standard numbers if it's one that we know, like 90 or 95%. And the confidence interval looks like P1 hat minus P2 hat plus margin of error, which is Z star times standard error. Now we have a new standard error formula. All these will be given to you on the exam. The standard error formula includes P1 hat and P2 hat. N1 and N2 are the two sample sizes. Make sure you take the square root of this thing once you do it, because that's a problem most people have, or a lot of people have when they're doing this. All right. Again, reminder, CLT is in play here. We have to have random independent sampling, a large enough sample, and a big enough population in both cases. Here's an example. Do people think that the space station was a good investment? To construct a 95% estimate interval for the estimated difference between the proportion of scientists and non-scientists. When we check this out, we find that there's plenty of big enough samples. We assume the population is big. Some things we can't know, we just assume. So we find a confidence interval for P1 minus P2 of negative 0.0658 and negative 0.0142. This interval does not contain 0, so that tells us there's a difference in the populations. And they're both negative, so that tells us that P2 is greater than P1, or P1 is less than P2. So the proportion of non-scientists is less than the proportion of scientists who believe that, and we think the difference in the proportions is between 1.4% and 6.6%. Another example worked out in the notes for you is talking about fracking, where they extract natural gas from rocks. And we did a confidence interval for this one, and it came out to be negative 0.014 and 0.117. Does that indicate a difference? Well, in this case, 0 is in that interval, and so we can conclude there is not a significant difference in the proportion of residents who support this technique in these two states. All right, let's work one out. Mars Candy Company claims that the proportion of red M&Ms is the same for plain and peanut varieties. Random samples of each showed this information. We want a 95% confidence interval for the difference in proportions of red in these two varieties. Well, there's going to be more work when we have two sample proportions, and you've got to be very careful with this. We do need the individual proportions, P1 hat and P2 hat, which these are worked out for you here. And our point estimate that we're going to use for confidence interval is the difference in these two, which is P1 hat minus P2 hat. Doesn't matter if it's positive or negative, we just keep it whatever it might be. Then we use a Z star of 1.96 based on the 95% confidence interval. That's where these comes from. And then we have our standard error formula, which I gave you on the page before, where we actually use this value and this value, and then the two sample sizes here and here. All right, so our confidence interval is the point estimate, 0.0263, plus or minus 1.96, times the standard error, and we get negative 0.1478 and 0.0952. All right, we're 95% confident that the true difference of proportion is between these two numbers. And since we're doing two proportions, we have to determine if 0 is in the interval. Well, in this case, because one's negative and one's positive, 0 is an interval, so this sample does not show a significant difference in these proportions. Again, the p-hats were different by 2.5 percentage points, a little over that, but that could be very much due to sampling. That's what this technique shows us. Is this different than asking if the data supports their claim? Absolutely. That's the question that's going to be raised anytime you have a hypothesis test. So let's look at how to do a hypothesis test for two proportions. Well, the process is basically the same. We have different hypotheses. One could be P1 equals P2, again, the equal sign in the null. Or some people are prone to write the second one here, which is P1 minus P2 equals 0, which those two are essentially the same if you look at them. And our alternative hypothesis is going to be not equal, greater than, or less than, depending on what we want to show. Our Z is going to be P1 hat minus P2 hat over the standard error. The standard error formula is different for confidence intervals and hypothesis testing for two proportions. Here we use a pooled estimate, which is P hat, to find the standard error. Well, we need to know what P hat is. So we'll talk about that in a minute. So we're back to the same setup, and we want to do a hypothesis test about the difference in proportions. We want to know if they're different. So our null hypothesis says that P1 equals P2. The alternative is they're different, which is not equal. P1 hat is 17 out of 90, P2 hat, these are all the same numbers we had before. Now, the P hat is different. P hat, if you can see, adds this number and puts it right here. And then it adds this number and puts those two right there. So it's the sum of all the successes and the sum of all the trials. We cannot average these two because that will not give us the right answer. We have to add the two numerators and two denominators, make a new fraction. So our P hat for this situation is going to be 0.2012. Again, our standard error formula that was given on slide or two before, we use that number in the standard error formula, and we come out with a standard error of 0.0618, which is similar to what it was when we did the other one. It was 0.062. Our Z is P1 hat minus P2 hat divided by the standard error, so we get negative 0.4256. Well, we're talking about trying to find not equal, so we do 2 normal CDF because our Z was negative. We're going to go from the negative end up to that value, and we're going to double it because of the not equals. All right, and then that gives us 0.6704. So this the interpretation is if the proportion of red M&Ms is the same for plain and peanut, probability is 0.6704 that we got these results. And because that p-value is much greater than 0.1, there's really not much evidence that the proportion is different between these two varieties. All right, another example. Suppose the Acme Drug Company did this to predict if this drug will help with people catching colds. And we want to find out if it's more effective for men than women. So our null hypothesis is that the proportion of people that got sick for both is the same. And the way I wrote mine is that the probability of female is less than the probability of male getting sick. You could do it probably from the other side of how many people were well, and it would look different, but that's the way I did it. And the numbers were given to us up here, the individual p-hats, and the difference in those two is there. Be careful with this p-hat, big p-hat for the standard error formula, because it gives us a percentage here and it gives us a total sample size here, 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 and here. So it says 38% of women, so that'd be 38 and 100, but 51% of men, which would be 102 out of 200. So we have to add those two together to get this proportion here. That would be one you could really miss if you're not paying attention. Won't kill you down the road, but be careful of you get the right numbers in this formula here. Well, now we have the standard error formula, and we use this value, not either one of the individual values, and we get standard error of 0.0611. Well, our z is the difference in the two sample proportions divided by that, and we get a negative 2.1277. Well, because we are using less than, that means we do to the left end of the chart, and we do a p-value, and it equals 0.0167. Interpretation is written out. We always have to state this. That tells us exactly what that p-value means. Well, now we have this p-value that is between 0.01 and 0.05. So there is fairly strong evidence that the proportion of females that caught a cold is less than the proportion of males. That's the basic hypothesis test. So this is the information that was just on the previous slide. And the question is, based on this result, would a confidence interval for the difference in proportions contain 0? Well, because there's strong evidence, fairly strong evidence for HA, that means just probably away from HO, which means HO would mean it would be in the interval. So if there's evidence for HA, then it's probably not in the interval. We're looking at this p-value, which is 0.0167, probably not contain 0. I did the interval, there it is, they're both negative, so 0 is not an interval. So we guessed that from here, but that's exactly the truth. You do need to make sure you can understand the difference between, the difference in what's going on with these two. Typically with two proportions inferences, you would not have to do both. You typically find the same information either way, but you could get a little bit of different result depending on the standard error formula because it's slightly different for the two different inferences that we're doing.